The materials can be organized into all kinds of shapes and sizes, but what we do know is that if they're all made from the same material, then they have the same Young's modulus. And this idea of Young's modulus is useful determining how stiff these different shaped and sized objects are. Here I have a wire of length L. I'm going to apply a force F to it, and this is going to cause it to extend by delta L. Now I have the same material wire, but now and the same cross-section area as well, but it's got twice the length. And when I apply the force F to it, this one's actually going to extend by 2 delta L. You can think of each section or L section as receiving the same force and therefore extended by delta L, so total extension is 2 delta L. So the longer the wire, the bigger it stretches for the same force. Here I have a wire with a diameter d, and I'm going to apply force F to it, and it's going to cause it to extend by delta L. Then I've got another wire here, which is the same material, so same Young modulus, and it's got the same length, but the diameter is twice as large now. When I apply a force F to it, what's going to happen? Well, that force is actually going to be spread across the whole larger area, so it's going to receive, each section is going to receive less force. So actually it doesn't extend as much. It only extends by a quarter of the length compared to the one on the left here. But why is it a quarter? That's because it's not the diameter that matters, it's the cross-section area that matters. So the first one, if the first one got cross-section area of A, the second one, well, we'll have to use the area of a circle here. And because the diameter for the second one is twice as large, that also means its radius is twice as large. So if it's got twice as large radius, and that's going to get squared, so actually the cross-section area is going to be times 4. So because it's got 4 times area, then that force is being spread. So the stress across that material is only a quarter, its extension is only a quarter. So why do I stretch less for the same force? Here I have a wire with the Young's modulus Ym, and then I'm going to apply a force which causes extend by delta L. And I've got another material over here which has 2 times the stiffness of the first wire. And I'm going to apply a force F to it, and obviously it's going to extend half as much because 2 times Young's modulus means it's stiffer. Okay, so the same material is stiffer, so it stretches less. So high Young's modulus means stiff material, so it stretches less for the same force. We saw that stiffness depends on 3 factors: the Young's modulus, the original length, and the cross-section area. In this question, we're asked to show that the stiffness constant K is given by the Young's modulus times the cross-section area over the original length. So let's start with the equation for Young's modulus, which is the most important here. So Young's modulus is stress over strain. Stress is force over area, and strain is change in length over length. I'm going to flip the fraction at the bottom and multiply like this, and that gives me this useful equation here. Now I need to bring in the stiffness constant. And if you look at this equation very carefully, it's actually here, force divided by extension. Because using Hooke's law, we know that a force is equal to stiffness constant times extension. So that means that the stiffness constant is force over delta L. So instead of force over delta L, I'm going to write K. Okay, then I just need to rearrange and I'll get the equation that's asked by the question. In this question, you have 2 wires of equal length and they're joint as shown in the diagram. So I'm going to annotate this information as I go through this question because there's a lot of information to process here. So they're both the same length. The bottom wire has a diameter d and a Young's modulus of ym, like this. And the top wire has double the diameter, okay, and the material it's made out of has doubles the Young's modulus. So that means it's twice as stiff. A mass m is hung on the end of the wire. The energy stored in the bottom wire is E. You can annotate that as well. Determine the energy stored in the top wire. Okay, because the mass m is acting through this whole system here, and we're going to assume the wires themselves have negligible mass compared to the mass at the bottom, the force acting through this all the wires here is F, which is mg, the mass times the gravitational field strength. Okay, now to compare energy, I can look at the equations for energy, elastic potential energy. So it's one of these. Now I know that the force through all of these is the same, and I don't really want to work out the stiffness constant, even though I just derived an equation for one. I just want to compare the extensions. Okay, so I'm going to use the first equation here. I could use the other one. Now I know half is just a constant, it doesn't matter. So is the force, is the same for both of those wires, so it doesn't matter. And I'm going to figure out the extension, which one's going to extend more. So to do this, I'll have to use Young's modulus in the rearranged form here. And I'm going to make delta L the subject. Okay. The force and the original length of both wires is the same, so that's not going to affect the proportionality here. The Young's modulus for the wire at the top is twice as much. Its cross-section area, now if its diameter is twice as much, its cross-section area is going to actually be times 4. because it's pi r squared. Okay, so at the bottom you have 2 times 4, which is an eighth. So the extension is going to be an eighth. So bring it back to the energy equation. If you have an eighth the extension, then energy is in the stored in the top. Y is also going to be an eighth. So it's 1 over 8e. The diagram shows a number of different wires made from the same material. Various masses are hung from the wires. Rank the wires from the shortest to the longest extension. Okay, so I'm going to use the Young's modulus equation again, but I'm going to rearrange it for extension, just like this. Okay, if I label the first one as delta L, I can compare what happens to the others just using proportionality. So the second one here, the one with 3m hanging on it, is going to have 3 times the force because of mg, so m is 3 times bigger, so the force 3 times bigger. The original length of both of the first one and the second one is the same, so I can ignore that. Cross-section area for the second one, because it's got twice the diameter, it's going to have times 4 the cross-section area. There's a square there. The Young's modulus is the same, actually the same for all of these wires because they're all made from the same material. So I'm just going to ignore the Young's modulus for this whole question. Okay, so 304. So that's going to have 304 the extension. Okay, now I'm going to compare the third wire to the first wire. Same material, so ignore Young's modulus. The force on the first and third wire is the same because they have the same mass hanging on them, so ignore that. The original length of the third wire here is times 2, twice as long. So it's times 2 there, and the cross-section area is actually going to be times 4 because it's got twice the diameter. So that's going to get squared. Okay, so it's 2 over 4, which is a half. So extension of the third wire is going to be a half delta L. Okay, finally comparing the last wire, it's got 2m hanging on it, so it's going to be times 2 the force. And the original length compared to the first wire is going to be times 2 as well. Cross-section area, now this wire has a diameter 3 times larger, so that's going to get squared, so that becomes times 9. So we've got 4 over 9 here. So 4 over 9 is approximately 0.44 delta L. So if we rank this with the smallest extension, it's actually the final wire, followed by the third, and so on. And so actually it's in that reverse order.